Short on local water supplies and long on regulatory requirements? Do a deep dive with us by listening to the Full Circle podcast to learn how Las Virgenes Municipal Water District and the Triunfo Water and Sanitation District are meeting 21st century water supply challenges for a portion of the Los Angeles and Ventura County regions.
Hello, everyone, and welcome back to our JPA Full Circle podcast, where we are discussing all things water and water reuse, specifically in the Las Virgenes Conejo region. Of course, this entire series has been Pure Water Project centric. This is the project that is due to bring us a new source of water, drinking water specifically, by 2028 via the advanced purification process. So at this point in our series, we have talked about a number of different topics within this project. We've talked about the regulatory impetus. We've talked about some alternatives that we were looking at, desal. We talked about AI last week. Now we want to get back to the science of the technology for this project. As I mentioned, the advanced purification process, it's this three-step process that is proven by science and heavily regulated to get this recycled water actually above our very strict and stringent drinking water standards. And so this episode, we would like to take a deep dive into that process. We want to see and talk about what makes it so effective. What are some of the constituents that are left in our recycled water that this process is here to solve for and treat out? And we're going to talk to some experts that have basically committed their lives to this science and making sure that it works to ensure a clean source of water is delivered. So we're doing things a little bit different today. Normally, we have our guests in person, but the experts that we have here today are super busy men and are all over the place doing their job and in very high demand. So we're very grateful to have them here today to talk about the advanced purification process and the constituents of emerging concern, those contaminants and things in the water that we don't want there. Some people know about them, and some are more popular, more well-known, such as pharmaceuticals. Some, such as PFAS, which we'll get into in a second, are a little less known for now. So we're going to talk about the experts that are ahead of this knowledge and that are working to make sure that we have the processes in place to solve for the issues that come up with water quality. So without further ado, since they can't be here in person, we're going to have them join us virtually via Zoom. And I want to take some time to introduce both of our guests. So first with us, we have Paul Swaim. Thank you for joining us, Paul. He is the Water Market Director for the U.S. West. Thank you for coming, Paul.
Thank you for having me. Looking forward to it.
And our second guest today is Larry Schmaler, and he is the Global Principal for Water Reuse. Thank you for coming, Larry.
Good to be here. Thanks, Ricky.
Yes, absolutely. So let's get into it. We have a lot to talk about for this episode. I mentioned we're getting into the details of the advanced purification process, but more specifically, we want to talk about how it is so effective at removing these constituents of emerging concern. Before we get into the questions and before we start picking your brains for your expertise in this topic, I just want to give a quick overview of what exactly a constituent of emerging concern is. All right. So in water, as I've mentioned several times in this podcast series, we like acronyms a lot. We have a whole textbook of acronyms that we're all given when we first start working in water to remember so that we can, reference them with ease. And so for the purpose of this episode, you will probably hear me say CECs in place of constituents of emerging concern, since that's a bit of a tongue twister and kind of a mouthful. So what exactly are constituents of emerging concern? Well, I will give you a definition as defined by the Water Board. Constituent of emerging concern encompasses any physical, chemical, biological, or radiological substance or matter in any environment media that may pose a risk to human and or ecological health and for which there is not currently published enforceable California or federal environmental or health standard, or the existing standard is evolving or being reevaluated, and or the presence, frequency of occurrence, source, fate, and transport, and or toxicology of which is not well understood, routinely monitored, and or may lack analytical methods. So that is a very long definition, but essentially these are contaminants that have a kind of known, maybe unknown impact on human health, on the environment, that we're just now starting to get an understanding of. So hence emerging concern. Some of these constituents of emerging concern include PFAS, which we're going to talk about in a minute, pharmaceuticals, personal care products, pathogens, flame retardants, disinfection byproducts, some pesticides, microplastics, nanomaterials, and biological agents. And these CECs are found in different water sources, soil, sediment, dust, air, and food. So essentially, they're very pervasive. They can be found pretty much anywhere. And once they are created, they are very difficult to destroy, and in some cases, remove from the environment. So now that we have sort of an overview of what exactly we're talking about, let's talk to our experts. Before we get into the science specifically, Paul and Larry, can you both sort of share your background with us in water and how you achieved your expertise in potable reuse?
Yeah, I think, Ricky, I'll go first and then Larry will jump in. So thinking back as a kid growing up in San Francisco Bay Area, the East Bay, we used to walk by there was a local filtration plant, water treatment filtration plant. We used to walk by in the evenings as a family, and I always wondered what was going on inside. And then I'd go out to play. I remember after it rained, I'd throw sticks and blades of grass in the flow down the gutter, and I guess I was conducting little hydraulics experiments of my own there. But
Definitely.
had a love for water. Decided to be a civil engineer, and I went to University of California, Berkeley in civil engineering. And first time I stepped foot in the hydraulics lab, I knew water was what I wanted to do for my degree. So after a bachelor's and master's and professional engineering degree, 30 years later, plus I've had the fortune to work on water and water reuse and disinfection projects around the world as a project manager and a subject matter expert. And on the reuse side, a project that Larry and I both worked on in Aurora, Colorado, after severe drought in the Southwest in the kind of 2005, 2006, 7 range was a career highlight on the reuse side. And after that, I got to work on projects in Australia and California, helped out in Singapore and across the United States. Kind of specialized in disinfection projects, working in Seattle and Boston and Chicago and Canada. Got to serve on an expert panel for New York City on their disinfection project.
Wow, you've been all over the country.
Had some fun, working on several billion gallons a day of water. And, as I said all that, or as I was thinking about what I'd say, I want to say that I don't know who listens to the podcast, Ricky, but any kids that are listening in and wondering about a career choice, working in water is the best. You get to do projects that protect public health and the environment, that are beneficial and have a positive impact on our communities. So we need water engineers and scientists and operators in the world. So if you're listening to this, it's a great opportunity for a career. I know you.
I could not agree more, Paul.
Yeah.
Yeah, and I'd like to add, anybody that works in water, especially at this point, I think we're all pretty enthusiastic about sharing why it's so amazing to work in water. None of us are hesitant to spread the gospel. So that should be a good sign for anyone out there considering a career in green careers or green jobs or environmental sustainability. Water is kind of where you want to be. Not biased at all. Okay, Larry.
Yeah, great start. I'm very passionate about water too, and specifically water reuse. So, I started my career right out of college in 1991, working actually on one of the most iconic potable reuse projects in the world. It's called the Upper Aquan Service Authorities in Northern Virginia. So that project had been supplementing and continues to supplement a local surface water reservoir since the 1980s for potable reuse. So I was ignorant at the time what potable reuse was. I had no idea how fortunate I was, but I got to work on that project, like the first project in my career. So, fast forward 15 years after that, I got to work on a bunch of other water reuse projects. And at that time, I then became our global technology leader for water reuse, which really opened up all these opportunities for me. I was able to work on, projects around the world, across the US. So I've worked on projects. So I've been with the company about 30 years, just like Paul, and I've been able to work on potable reuse projects in, California, Colorado, Virginia, Florida, but also internationally in Brazil and Australia and in the UK. So a lot of great opportunities, super fun place to be working in. I've also been able to do some water research projects specifically around water reuse for the Water Research Foundation. So a lot of interesting scientific studies around water reuse, and then been involved in development of some of the regulations around water reuse. So,
awesome. Oh, very nice. That's literally why we have you here today. Is it safe to say then, Larry, that water reuse kind of found you?
It did. Yeah. Good way to say it. It exactly did.
That's awesome.
I didn't even know it at the time. Yep.
Exactly. That's how it works, right? Water kind of finds you. Well, we're excited to have you both here. It's very clear why you are the leading experts in this topic. And so I'm really excited to pick your brain when you talk about these constituents of emerging concerns, specifically because they're not well known by the general public. It can be kind of intimidating addressing them and sharing the knowledge that we do have and the information that we do have. But what we want to know is that this process that we are using for the Pure Water Project is in fact successful in removing some of these constituents, right? So, before we get to how it is, let's first kind of dial it back. I provided a very lengthy definition of what a constituent of emerging concern is, but can you kind of share with us, in your words, what exactly CECs are and what we know now about how they affect us and sort of what are the most common ones?
Yeah, I'll start off, and then I'm sure Paul can chime in there on that question, Ricky. Yeah, that was a lengthy definition. I wrote down some keywords in that definition. I think I've heard that once, but it's not, commonly in my brain. But you mentioned physical, chemical, biological, radioactive. Oftentimes when people talk about CECs, it's really focused on the chemicals, like you said, PFAS, and not necessarily biological agents, although that certainly can be. But the way I think about CECs, it's regulated and unregulated chemicals that are in our water supplies, and they're referred to as emerging. The chemicals of emerging is concerned, really because of the advances in analytical equipment, analytical chemistry that allow the measurement of these chemicals down to extremely low levels. So these chemicals have really always been present in the water for decades, since we've industrialized the world. But now we're able to measure them at very, very low levels, nanograms per liter, just crazy low levels that we can talk about.
Our science is getting better, right?
Yeah. The analytical chemists, the equipment they use, they're able to measure these at extremely low concentration. So, many of the CECs that are present in our, like you said, air, soil, water, wastewater streams. For water, it's specifically, like pharmaceutical and personal care products, maybe that you ingest, but you don't completely metabolize. Then they get passed down into the wastewater. So it's things like, sucralose. That's an artificial sweetener people use in tea and coffee, right? Splenda packets. Yeah. So that's very common in our water because it's not highly metabolized, and it can make its way, in the water streams. When you go get an X-ray or an MRI, you often ingest like iohexol, iopimidine. Those are X-ray contrast agents that allow the medical procedure to perform adequately. So those chemicals can make their way into the water stream as well. And then there's drugs like carbamazepine. It's an anticonvulsant medication people take for when they have seizures. Mm-hmm. So a lot of these things, can eventually make their way into the water. So, but I think it's important to note that just because we can measure these CECs doesn't mean it's a health risk, right? It's just that we're being able to measure these at extremely low levels, but we want to take it seriously. We want to, provide a multiple barrier treatment approach to make sure we remove these chemicals through the advanced treatment process.
Yeah. So I wanted to pick up on something Larry said related to the analytical chemistry advances, and just thinking back on where we've been with regulations of of wastewater and reuse and drinking water. And when the U.S. passed the Clean Water Act, and I think it was 1972, we started looking at discharges to waters as point sources, and we were measuring milligrams per liter. We were looking at total suspended solids or organics at a part per million type concentration. And similarly, the Safe Drinking Water Act, in that same era in the 70s, we were looking at solids and turbidity and specific compounds at parts per million and sometimes parts per billion levels. But when we talk about CECs, we're talking about maybe parts per billion and often parts per trillion levels. So very different kind of just orders of magnitude of concentrations. And so we've got safe water, and we've focused in on, well, what else can we think about and what's next? And that's where CECs come in.
Yeah, and we'll kind of dive into what exactly those terms mean, right? Like parts per billion, parts per trillion, in a little bit. But before we get into that, let's talk about who regulates this process and who is involved in creating these regulations. Can we kind of get into that? Who kind of governs over this science, I guess?
Yeah, excellent question. It's highly regulated. So California's State Water Resources Control Board regulates potable reuse in the state of California, and then their Division of Drinking Water, it's called, is the group that specifically focuses on potable reuse and identifying the advanced treatment processes that are required to remove these CECs. So, during development of the surface water augmentation regulations, those are the potable reuse regulations that Las Virgenes will fall under. The state actually, when they're developing those regulations, they actually convened an expert panel, a technical expert panel, to review the state's proposed criteria for potable reuse. So they convene a group of 7 scientists. I think there's, a chemist, microbiologist, a toxicologist, a limnologist, water and wastewater engineers, all these experts. And they determined, after evaluating the state's criteria and analyzing it in detail, that yes, this is protective of public health. So they determined at that point in time that the regulations that were established for surface water augmentation were very protective of public health. So then the state actually went above and beyond that, and they developed what's called the recycled water policy, which requires monitoring of numerous CECs on a regular basis in the finished water to ensure that the safety of the water is there. So they look for things like sucralose and iohexol that I mentioned before to confirm that the treatment process is functioning properly and removing those constituents. And on top of that, they also require online surrogates to be measured. And we can talk about this in more detail, but things like total organic carbon, which is it's a surrogate, but it can be measured real time. So you can measure that on a consistent basis, a continuous basis, to confirm that all your treatment is working well and is removing these chemicals from the overall process.
Dial it back. What do you mean by surrogate? Is this like a byproduct or something?
No, surrogate is a representation of the chemicals, but it's not the actual chemical itself. So it's a measurement of a bulk water parameter that's easily measured. So we can measure the total organic concentration. So it's the total organic, all the organics present in the water. That's actually a pretty easy measurement to make, but it's a representative of. If it's a very low value, then you can say, yeah, I'm removing my chemicals quite well. If it spikes up and hides, and then, well, maybe we have a problem, let's shut down and we'll investigate the issue. Go ahead,
you
Paul.
want to measure something that's indicative of, that's going to be an early indication of any problem, right? And you want to measure something that's easily measurable. So that's what Larry's talking about.
So it's like
Larry,
more accessible.
Yeah, exactly.
Yeah.
But Larry, when you talk about the regulations, there's a fundamental premise of those regulations, and that's that the treatment facility have multiple barriers, right? So you want different treatment approaches to do different things through the treatment process. So it's, reuse regulations are built around that premise. Our drinking water regulations are built around the same premise. Like we regulate surface water treatment for drinking water. If you think of the Colorado River or other surface waters, you have to have several steps. Normally you'd have filtration, you'd have disinfection, different barriers, physical, chemical. That's the underlying premise of our U.S. Water regulations as a whole.
Yeah, it sounds very different from what one may think toilet to tap is, right? It is multiple steps with multiple cycles, definitely not just one end to another in one fell swoop, right? So, can you quantify sort of how long it took to create these regulations based on the science, right? We talk about this advisory panel. I mean, how long did that process take?
A long time. California they started practicing water reuse in the 1960s. And I can't remember when the first draft of the water reuse regulations was implemented, but I believe it was in the 1990s.
Mhm.
And then they finalized the surface water augmentation for potable reuse regulations in 2018. They've been in development and discussion and research and expert panels. I mean, it's been studied to death. It's very good. I mean, the science is very strong, and lots of people have overseen it. So excellent job by California regulators and pushing out these regulations.
Yeah, and that's so important, right? Because when someone hears of something for the first time, or the public is, first made aware for the first time, they think that it's like a new technology or a new science, a new cycle. They don't understand oftentimes the decades that, went into developing, studying, doing the research, like you said, all the R&D, getting to the regulation. So it's really important that we emphasize that this is something that has been researched and in development and in the works for decades, so that people can trust that this isn't just some new thing that we sprung on them and we're, using them for guinea pigs. That's a huge part of our outreach for this project, especially.
Yeah, you can go back and look at textbooks and journal articles, technical journal articles from, the 1980s talking about potable reuse and the science that needs to be developed and advanced to support safe potable reuse.
Yes.
So there's a long story there for sure on potable reuse.
Hey, for anyone that's interested in going through decades old technical texts, it's right there for you. If any skeptics out there, if you'd like to decipher that for the rest of us and not get paid for it, unless you're professional, have at it, right? Okay, so let's dive into the process now. First off, what exactly makes advanced purification process so effective at treatment for CECs?
Yeah. So what we do in California, we have a process we call full advanced treatment. And building on what we were talking about there, it's a multiple barrier process. And it's a multiple barrier process in a couple ways. So, when you look at Las Virgenes' Pure and Triumpho's Pure Water project, there's a number of different elements there. So first, the wastewater goes to the Tapia Water Reclamation Facility and gets treated at a wastewater treatment plant.
Right.
And you've got filtration, and you've got disinfection, you've got primary treatment, secondary treatment.
Mm-hmm.
Then you bring that water over, the excess water, to what we call an advanced water purification facility. And that's where you have the full advanced treatment. And at that step, you've got membrane filters, reverse osmosis membranes, and then a third process, ultraviolet light-based advanced oxidation. And we'll talk a bit more about those, or I can talk a bit more about those. But after those processes, the water goes on to Las Virgenes Reservoir and is subject to natural factors like sunlight and retention time. And then after that, the water gets extracted from the reservoir and goes to the Westlake filtration plant with more filtration and more disinfection. So there's kind of two elements of multiple barriers. One is the different steps that the water goes through. The other is the treatment itself at the advanced water purification facility. So sometimes we tend to focus on the advanced water purification facility, but that context of it being one of the barriers along the way for a project like this, mm-hmm. bringing the water full circle, as I know is the slogan. It's just that facility is only one of the steps.
You name dropped our podcast. That's amazing. I love that. It's important.
So if we talk about the advanced water purification facility, so we have membrane filtration that's focused on removing particles, solids, pathogens, and then we go to reverse osmosis, and we're forcing the water through a semi-permeable membrane with pressure and removing more pathogens or remaining pathogens and most other constituents, salts, CECs, inorganics, organics, metals, PFAS. you name it, we're removing it through the reverse osmosis. And then we go to ultraviolet advanced oxidation, and that's my favorite process. You've got photons of energy that are being produced into the flow of water, and they're going to reach molecules within the flow. They're going to do two things at the same time. One, they're going to just destroy compounds directly through they call it photolysis, of the energy reacting with those compounds that are remaining. And then secondly, you're forming a very strong oxidant that's going to break down other compounds in the flow. So you get kind of two barriers in one, the effect of the energy itself and then the oxidation that occurs. So back to the multiple barriers, you've got various different processes and mechanisms there. And that's what makes it so effective at removing CECs, is that different mechanisms and stepping one after the other through the treatment process at the advanced water purification facility.
Very nice. So this process is expected to remove many different types of CECs, right? Of many different makeups. So what are some of the parameters or mechanisms involved in measuring the effectiveness of CEC removal during this process? What makes this reliable?
Yeah, so I'll jump on this one, then Paul can probably chime in too. But the FAT processes that Paul mentioned, the full advanced treatment process, microfiltration, reverse osmosis, and UV advanced oxidation, they all come with online analyzers. So we have analyzers that are attached to the pipes that the water is flowing through, and these analyzers are measuring on a continuous basis certain concentrations to confirm that each individual unit operation is functioning properly. So a good example is, you can use what's called a conductivity probe, and that measures the electrical conductivity in the water, which is a surrogate. It represents the amount of salt in the water. So you put one of those upstream of the reverse osmosis, and you put one downstream of the reverse osmosis, and you can calculate the percent removal across the RO on an online basis. So every minute of every day how well the RO process is at removing dissolved salts in the water. So that when you have that verification, then you can be confident that your RO process is also removing the pathogens Paul mentioned, the CECs that are present, and you're getting excellent removal of all those constituents. So each of the unit operations has these analyzers to confirm the performance, and the regulators call this critical control points. So every treatment process has a critical control point to confirm that you're getting the individual unit operation is functioning properly.
Or multiple critical control points, right? So Las Virgenes has been running a demonstration plant as well for these treatment processes since I think late 2020. And they've done a number of sample events for contaminants of emerging concern through the treatment steps, and the results are, match up with the literature, and we're removing, for the most part, all CECs down to detection limits. There's maybe a couple of compounds, one Larry mentioned before, sucralose, that you're not getting down to a detection limit. It's reduced through treatment and removed, but it's still at measurable parts per trillion concentrations from those sampling events, but it's at levels way, way below what'd you say, Larry, put it into your tea if you were looking for an artificial sweetener.
Yeah, I think, Splenda, for example, a packet of Splendas is 12 milligrams. The concentration Paul's talking about is like 12 nanograms or even lower than that. So it's, what is that, Paul? 1 million times lower is the concentration that may be present in the water. So it's just because, as we talked about before, the analytical chemistry has gotten so accurate, so precise. You can just measure these extremely low concentrations, but it really has no health relevance at all.
Well, I know we're talking about, oh, sorry, Ricky.
Oh, no, go ahead.
I was going to say, I know we're talking about CECs, but the decades that Larry walked through of developing regulations, a lot of that focus was on pathogens and removal of viruses, removal of Giardia. That's, we worry about when we're camping, right? And you're filtering your water, focusing on cryptosporidium. That's really the bulk of the regulations are focused on how do you remove pathogens, because that's about acute safety, right? Acute public health, that you don't want to drink water with pathogens, you're going to get sick. So the regulations focus on that and require significant levels of reduction of each of those types of pathogens, viruses, Giardia, Cryptosporidium. In fact, it's 12 log virus destruction, so 12 order of magnitude removal, and 10 for Giardia and Cryptosporidium. So I know we're talking about CECs, but the regulatory construct's really written around both pathogens and CECs.
Yeah, I'm glad you kind of highlighted that, because in certain parts of the country, certainly in certain parts of the world, these pathogens still cause huge human health crises. You know what I mean? And so obviously this process, one thing that we're also being able to cover and solve for are the CECs, but these are still, the pathogens are still issues that we have to make sure we can solve for. So kind of killing two birds with one stone with those regulations, definitely. So you guys talked about pathogens a little bit. Before I ask this next question, though, I kind of want to introduce PFAS into the conversation properly. And so when we give tours of our facility and we talk about reverse osmosis specifically, that second step, we highlight or kind of what PFAS is. Many people still don't know what it is, but it's definitely been in the media more lately. So I think it's kind of just now coming into public consciousness. Can you sort of highlight what PFAS is and what we understand are its human health impacts?
Yeah, maybe Larry, you want me to start and you can chime in? So,
Yep.
So PFAS, PFAS is per and polyfluoroalkyl substances, which the newspapers, the media talks about forever chemicals, right? No one wants to say what I just said. So forever chemicals, and really the focus on the regulatory side is on two specific types of forever chemicals: PFOS, PFOS, perfluorooctane sulfonate, and PFOA, perfluorooctanoic acid. So those are kind of the focus, but there's lots of different species or types of PFAS. The good news is really well removed by reverse osmosis. So the multiple barrier concept works really well, and we're removing anything that's in the water. Think about cooking with, a coated pan or something like that, or running your dishwasher then, or washing your dishes, or the laundry you do on, waterproof clothing. That's where it's coming from. It's measurable, again, with the analytical chemistry advances in our wastewaters. And then, like I said, the reverse osmosis treatment step in particular does a really good job at removing those forever chemicals at an advanced water purification facility.
Yeah, we've studied PFAS concentrations before and after reverse osmosis, and consistently have seen in the RO permeate, is called, after the RO treatment, the permeate, the concentrations are below detection limits of PFAS. So it's an excellent barrier to removing those PFAS compounds of the RO is.
Yeah, and I'm glad you kind of gave us that overview, Paul, because it's really important that our listeners and anyone that will be drinking this water in the future understands we, the water agencies, we do not put PFAS in the water, right? The PFAS ends up in the water by, all the methods you mentioned: rinsing off your, nonstick pans, washing your clothes, eating and drinking and using the restroom, because PFAS is in all of these things. And so it goes through us, it goes through our tools and materials, and then it ends up in the water. And this is the process that allows us to remove it, right? And so, Paul, you sort of spoke to this a little bit earlier, but can we talk about some of the limits for PFAS that you often hear? So you mentioned parts per billion, parts per trillion. Can you give context to those terms to help me and our listeners understand what exactly that means with regards to human safety?
Yeah, I mean, context is important, right? So I don't have that. Maybe Larry has the exact limits handy that are being discussed, but they are parts per trillion level. And so, I talked about the progression of regulation from parts per million to parts per billion to parts per trillion. So it's kind of tempting to try to put that in terms of money, but I don't know what rabbit hole that would go into. So right. Larry and I were talking about, let's talk about time. Okay, so a part per million is 1 second in 12 days. So we just elapsed that second, right? And over the next 12 days, that's a part per million. So that's a drop in the bucket, right?
Right.
A part per billion is 1 second in 32 years. So 1 second in Larry's career, we just elapsed there. So much different time scale than 12 days. And then if you think about a part per trillion, that's 1 second in almost 32,000 years.
Wow.
So that's at an 80-year lifespan, that's 400 lifespans. So
wow.
1 second
I've never
in 32.
heard it explained like this. That really puts a lot into perspective.
Yeah, so well beyond our lifetime and anybody that will remember us as lifetime. But yeah, so drastically different numbers, right? And the scale is sort of overwhelming.
All right. So as experts yourself, what would you say to customers who are still understandably skeptical about the safety of water that comes from this process, especially those that are used to the tap water that they drink or the bottled water that they drink, perhaps?
You want me to jump in, Larry?
Sure, go ahead.
Okay, so I mean, I hope they're drinking tap water because tap
Right.
water is very safe and much more environmentally sustainable and friendly than bottled water. My house, we drink a lot of tap water. My daughter's a cross country runner and she's always rehydrating. So we fill up our water bottles all the time and put them in the refrigerator. But the purified water we're talking about that's going to go through our advanced water purification facility for Las Virgenes, and then the reservoir, and then the drinking water plant, it's going to exceed all federal and state drinking water regulations. So it's going to be safer than, or as safe as the tap water when it's served. I've been on Ricky's tour a couple of times of the demonstration facility and had a glass of the purified water without hesitation. It's good stuff. I'd be happy to have it as my water source and I'd serve it to my kids and with no hesitation.
Yeah, I'd second that. I would drink the water in a heartbeat, and I have in the past on many projects, and potable reuse projects. The science is sound. Everything that's gone into it is sound. But I think it's like you said, it's understandable for people who are skeptical, and I think it's good to seek out these answers. Right, when you come across a problem that you're not familiar with, an issue, it is good to seek out the answers from different sources. But I think given the amount of technical scrutiny that, we talked about the regulations, there's tons of technical scrutiny that went into that, the validation of the treatment processes and all the monitoring that's required for through all the different advanced treatment processes. I think, I could comfortably say that I'd highly recommend this water to anybody and my family, my kids, everybody in the public. It's very safe water.
Yeah, I would agree, obviously, because I'm the one giving the tours to the public and to anyone that's interested. And nearly every time I like to do the tasting with our customers. I mean, really and truly, as you mentioned, Paul, I would love to have this as my water source. The purified water itself, like the advanced treated water, I mean, that's some of the best tasting water I've ever had. Right. It's really soft. It hasn't been mixed yet. So you can't taste any effects of the, minerals that we add for, safety. This is a really high quality of water. As a matter of fact, there is a Stanford study that was done, correct, on water that comes out of this advanced purification process. And it's found that it's some of the cleanest and safest water that you can get pretty much anywhere from any drinking water source. Right. So this is something that has been researched. I mean, it's been co-signed by Stanford scholars. So I think that if myself and you, Paul and Larry, are experts, can trust this process and trust this water, and we have the context of the scientists that help to shape the regulations, that worked on that R&D like you, Larry, for all those decades, that people can trust that this is a reliable water source and something that we can and will need to lean on into the future to make sure that we have reliability in our water service, that we are taking care of any rising water quality challenges with, CECs, and just making sure that we're making use of the innovation and technology before us, right? I mean, we know that the water cycle is effective at recycling the water for us, but we also know that it takes some time. And we have many, many, many more billions of mouths to feed on this planet now than we had, thousands of years ago. So we can't just rely on these natural processes. We have to use our big brains, or I should say your big brains, to help us come up with the innovation to essentially make water and speed up these processes.
Yeah, amen. Very well said. And, couple that with, the droughts that we experience on a periodic basis. We've seen a lot of them in California. We've gotten a lot of atmospheric rivers this year, but in the past, it's been a lot of droughts. So that, as you said, to increase the reliability of our water systems is becoming more and more important to be practicing potable reuse in many communities.
Thought I should mention that, Las Virgenes convened what they call an independent advisory panel in 2018. Dr. Childress from USC, Dr. Anderson, a limnologist, Dr. Bull, a toxicologist, Dr. Mitch from Stanford, that I think was part of the study you mentioned, Dr. Verbala from San Diego State. That panel, heard all about the project and said it was going in the right direction and following the regulations and in that way endorsed the work. That panel is going to be, I believe, reconvened again this year to talk further about the project. And so that's another step in the regulations that Las Virgenes has sought out and convened through the National Water Research Institute to bring independent perspectives to the project and make sure that Las Virgenes and the Pure Water Project are going above and beyond what's required.
Yeah, that's a really good point, Paul. I think that it's important for our customers to be able to get that reassurance of the safety of these processes and the water that they're going to be drinking and serving their kids from multiple sources. And so I'm glad you brought that up, because that is something that the JPA is going to reconvene, like you mentioned, and bring back. Again, just in the name of making sure our customers are thoroughly informed and educated and can rest assured that this water source that they're going to be drinking in just a few years now is beyond standards. So I'm glad you mentioned that. And I'm so happy that both of you found time in both of your busy schedules to join us remotely for our special remote episode of our Full Circle podcast. I really appreciate you taking the time to share some of your expertise surrounding advanced purification and water reuse in general. Thank you both for joining us and continue to go forth and lead us into the future of water and sustainability.
Thanks, Ricky.
Thank you so much, Ricky. It's been a pleasure.
Yep.
Yes, thank you both. And for our listeners, I want to thank you again for joining us for this episode of the Full Circle podcast. Hopefully you were able to get some clarification about this process as it relates to these constituents that I'm sure you've been hearing about, that you have questions about. If you have any more questions, our door is always open. Come to a tour, come learn about the process, come look at it up close and personal. You can talk to our on-site staff, some engineers that we have here to help you clear up any questions you might have. We want to always lead with transparency and make sure, again, that our customers and our listeners are as well informed about this process and can have some of their concerns addressed, all of their concerns addressed. Again, thank you both for joining us. And we will be talking about this process from an operator perspective, those of the employees that are actually on site, working with the process, working with the infrastructure at our next episode. So thank you again for joining us for a special remote episode of the Full Circle podcast, and we'll see you next time.
Thank you for listening to this episode of the Full Circle podcast. Make sure to follow us on Twitter at LVMWD, on Instagram at Las Virgenes_MWD, and on Facebook at LVMWD. Find our Full Circle podcast on your favorite streaming service, or go to ourpureh2o.com and smash on the Full Circle podcast link for all other episodes.